Hello everyone, and good afternoon, and welcome to this session. My name is Timothy Hunter, and I'll be very happy to talk to you about how to combine different machine learning frameworks with Apache Spark. So let me introduce myself briefly. I've been using Spark throughout my PhD thesis at UC Berkeley for a while, so since before Spark was an Apache project, and now I work as a software engineer at Databricks. So let me give you a few words about Databricks. It is the company that was founded by the creators of Apache Spark. And it provides a hosted platform that provides Apache Spark in the cloud, and which you can manipulate after that through notebooks. You can run these notebooks in jobs, and you can manage clusters of Spark clusters through a web interface. So you are probably aware by now of Spark, and it has become now one of the most active open source projects in the field of big data. And in January 2016, it featured more than 1,000 contributors, and this number keeps growing. So this talk today will be about machine learning, and in particular the integration of Spark with other frameworks, including also the machine learning component that is embedded inside Spark, Spark MLlib. So MLlib is the library that provides large-scale machine learning solutions to Spark. And its mission is to make machine learning practical, easy, and scalable. So the goal of MLlib is to make sure that you can easily build some machine learning solutions that are useful for data science team or data engineering teams. Also, of course, because this is Spark, that it should work with large-scale data sets. And also, I think, but to me, it's really first and foremost, MLlib's mission is to make sure that it does not disrupt existing workflows and procedures within data science teams. And when we talk about machine learning, usually it's a very broad scope of algorithms and challenges. And this is why now MLlib keeps adding new algorithms and solutions. As of now, there are more than 27 transformers for transforming your data and 20 algorithms implemented. And in this slide, I highlighted in bold the new algorithms that have been contributed by the community since Spark 1.6. So you can see it grows at a very healthy rate. And in particular, the generalized linear model, which is underlined, has been a huge contribution from the community for Spark 2, which is due to come soon. So, okay, today I will mention today will be about machine learning workflows. We'll see why they are so complex and why it makes sense to use Spark in this case, even though you don't necessarily have a large-scale data sets. And then I will explain how you can, I'll show you a few examples in which, even though you may not think that Spark is actually relevant for that problem, it is actually something that, it is actually a tool that can be beneficial for some of your machine learning problems. And finally, I'll talk a bit more about MLlib. So if you have been working in data science or in data engineering, you're already familiar with the complexity of machine learning workflows. And usually, when you give a task to a data science team, they usually have an idea of how to solve it. But first of all, they need to specify the pipeline through which they will run the data. They will also need to rerun and inspect the data that is being processed. And there is a lot of ad hoc steps in which you need to be able to inspect the intermediate results, figure out what to change, figure out what to do. And as in machine learning in general, there is always a few knobs to tweak and a few parameters to tune. And if you don't do that, this is usually the difference between having a working and efficient solution towards getting essentially garbage at the end. And usually each of these steps in a machine learning pipeline has been addressed in a way or another by different solutions. And a lot of time is spent making these different frameworks and these different libraries communicate with each other. And we'll see how Spark can help in this respect. So what I mean by complex data pipeline? Well, usually you have a couple of data sources for which you need to extract features. These feature extractions themselves usually can be fairly complex and costly. For example, if you want to use neural networks and eventually you have usually some ideas of a model that you would like to train at the end. And for robustness, usually you don't train one model. You train several of them, and then you try to combine them together. So then that also increases the complexity of the whole solution. And this is not even counting after that the evaluation step, for which you check that the business metrics you're trying to optimize are actually being optimized. And usually you realize not necessarily the case, and you have to go back to the drawing board and iterate again and again on this pipeline. So for that, there are some very good and well-established tools that have been developed for single machines, because this is not a new problem. Here I highlighted a couple of open source solutions that people are usually familiar with. And Scikit-Learn is a standard machine learning library for Python developed by Google. R is the well-known workhorse for doing statistics. And Pandas also is a very popular solution for doing data manipulations. So usually when you have a team of data scientists, they are well aware of these tools. There has been a lot of training and tooling being developed for these solutions. And when you want to move to larger data set, or even if you have some small data set, you would like to be able to leverage all these skills already acquired. And today I would like to talk about two common misconceptions that we see when people talk about Spark. The first one is that Spark is useful only when you are dealing with big data. And we'll say this is not necessarily the case. And the second one is that if you want to integrate with Spark, you should always think about large distributed scalable algorithms. And usually this is not necessarily where you get the most, well, you can get a lot of benefit from Spark just by using some libraries that have been designed for single machine frameworks. So let's see a first simple example in which you want to run a lot of tasks in parallel. Because if you look at a lot of machine learning tasks, they are what is called embarrassingly parallel, in that you can run all of them separately with different chunks of data. And for each of them, you can then combine the results later. And you don't need to have them communicate necessarily in a very complex fashion to solve their problems. And Spark excels really in this case for doing data management and for doing scheduling. So let's take an example which seems to be quite antithetical to what people think about, to what people think usually. Let's consider, for example, a common task in computer vision using neural networks, in which you want to learn digits from a set of images. So this is one of the most standard benchmarks you can see in computer vision. So when you have small images of digits, and then you want to figure out what is the actual number represented in it. And the most common way of addressing this problem for right now is to use deep learning algorithms or neural networks. And training a neural network is hard for a number of reasons. The most relevant one in this discussion here is that training a neural network is essentially a sequential operation, because you need to feed into the neural network during the training phase. You need to feed one image after the other. And you get some benefit from trying to parallelize it, but it is still a big research area over there. So really, you would think, how can I distribute that? However, it is also very sensitive to the way you present the images and to some noise. So when you want to run these, when you want to do these training phases, you usually want to make several passes over your data with slightly different parameters to figure out how sensitive your parameters are going to be to the noise and to see how robust your solution is going to be. But mostly, I think that the most important facts about deep learning when you training deep neural networks is that you need to tune for an extensive amount of time the parameters that you use for during the training. For example, you need to have very specific descent rates, batch sizes, and some other parameters like this, or for example, or sizes of your neural network. And if you don't do that, it will either never converge in a reasonable amount of time, or it will converge very quickly to something that is irrelevant. And figuring out exactly which are the good parameters is what makes a difference between working or not in practice. So in this case, I'm going to run a simple example using TensorFlow, because there has been a lot of machine learning libraries offered for doing neural network training. TensorFlow is one of the newest, and it has been open sourced by Google about 6 months ago. And it is a very popular choice for doing neural network training. And up to a month ago, it was essentially just a library that would let you do sequential training. And more relevant to Spark, it has a very good interface in Python, which means it is easy to integrate as a single machine Python package. So really, how could we get some benefits from using TensorFlow with Spark? Well, even if it is a single machine library, as I was mentioning before, we need to train these parameters, and it is not clear from the outset which ones are going to be some good set of parameters. So you actually are better off launching multiple experiments all at once on a cluster. And you can use Spark as a scheduler and as a data processing engine, as a data ingest and ingestion engine for these libraries, and let them all run and figure out what would be the best model you would achieve at the end. So very simply, so in this case, you can simply have, usually this data set is, or in that case, this data set is small enough that you can simply broadcast it across all the machines and then run with different parameters of descent rates, neural network sizes, some experiments to figure out what the best model is going to be. So what kind of speed up can you achieve with this? So in order to achieve the same final results, the same performance, if you were to use just one computer, so in this case, this is not using GPUs, but you would get the same speedups with GPUs. So if you were, we ran this experiment on a single node, and then we increased the number of nodes available to Spark. And as you can see, you can get some very nice speedup, although not quite linear, but you can get some very nice speedup from just from using a single node. And you can go from running experiments during a few hours down to about 20 minutes for the end, which is essentially the time it takes for running just one experiment. And this works very well if your computations are CPU bound and in which you want to try out a lot of different parameters. But so to recap quickly this part, even if the algorithm is essentially sequential, there is usually some parameters that you need to carefully select in order to get a good solution. And Spark can help you for that in doing fast iteration over what would be a good set of parameters to explore. But this is a bit brute force. And let's see really how we can actually have a better level of integration with other libraries. So if you're a data scientist, what are you really hoping for when you are working in a team? The first one is to make sure that the code you are running would be hopefully the same as the code that you're going to deliver to then to the production team. The next one is that usually you have your company has some ways of storing your data in a single source. So you'd like to be able to use distributed data sources. Then of course you would prefer not to have to learn again some new sets of libraries. And finally, it is very common to have some pieces which are easy to do on a local machine. For example, introspect data, sample data. For example, if you're familiar with IPython and you would like to be able to run things locally, and you would like just to be able to distribute piece by piece all the pieces of your workflow that needs really this distributed setting, and keep the rest locally and close where you can do fast iterations. So only distributed as needed, and then hopefully be able to switch back and forth between a local and a distributed setting. So let's take a quick example here with Scikit-Learn and Python for doing a simple task, which is a sentiment analysis. So here I have a small data set coming from a set of Amazon reviews, and you can see some ratings associated to the text of the review. And what we would like to do is, given the text of the review, infer what the rating was. So you can see there are some good ratings. Some of them are, well, definitely not as good. Let's see what we can do for that. So in a typical, as a typical pipeline and a typical workflow, you would load this data. You would convert this data into some numerical forms that are more amenable for machine learning algorithms and for training models. Then, given a model, you would train it. And finally, you would evaluate how good this model is. So we have seen a lot of people using Spark just for extracting the data from their sources because it includes a lot of built-in plugins. It includes a lot of built-in features for reading different sources. For example, Parquet, JSON with schema inference, but also, of course, Hive, MySQL, S3, and so on. And also, the Spark community has been very helpful in developing a lot of other plugins for talking with different sources. And all of them are available online and very easy to add as a Spark plugin. So once you have used this data, you want to be able to convert it to some form, to some vector form. Since this is text data, there are some standard tools for doing that in this case. In this case, you could tokenize it, so separate each word by itself, recognize the words, and then weight the word depending on how frequently they appear in your data set. And for as a model, let's pick linear regression because it is a standard model and it is fairly robust to all sorts of noise. So we will start from feature extraction and then do some model training. And for the model, so this is again when Spark can be useful here. When you do model training, you need to usually try different parameters to regularize your data because your data is going to be noisy. It is not clear how much of it is, which words are going to be relevant for figuring out what the rating is going to be. And so you want to be able to regularize the model. But it's not clear which is the best parameter for doing that. So there's a standard procedure called cross-validation that lets you try out different parameters and see how well they fare on some other pieces of the data set. And this is all implemented as basic primitives inside Scikit-Learn. So Scikit-Learn is a single machine library, but yet again, we can actually integrate within Scikit-Learn some operators which under the hood let you distribute the computations and bring back the best model. So you would start with your data set, for which you could do all the feature extraction in Scikit-Learn, and then run in parallel different models for doing the cross-validation. And finally, you can let Scikit-Learn do the extraction of the best model out of that, and just use Spark under the hood within your pipeline. So let's see. I have a quick example here on what it means. So I have here notebooks in Databricks attached to a running cluster. And I'm going to launch, So I'm going to do a few imports here. First, I'm going to load the data, some pieces of the data from this data set. And I'm going to convert it to a pandas data frame, which is the standard way of representing data in Python and Scikit-Learn. So right now, it is reading it from S3, which is why it runs on Spark jobs. Let's see what we have. OK, so we have a bunch of reviews. Oh, someone's having some problems with their laundry room. Oh, dear. Let's see. So this is a small data set. It only has about 17,000 reviews. And let's make some shortcuts here from the pandas data frame. OK, so now I'm going to build a pipeline here using Scikit-Learn. So let me launch it because this one is going to take a while. So as I was explaining, this data is going to come from a data frame, and first it's going to be transformed by vectorizing the data, then doing a quick analysis to figure out which words are the most frequent, to discount these words. And finally, I'm going to run an algorithm at the end. I'm going to run linear regression. And I'm going to do a grid on a number of parameters. So here I'm going to run it on 20 different regularization parameters. And right now it is using the local computer to run all these experiments for different parameters locally. And this is why, it is just using the few cores on my computer. So it is going to take a while. I think it took a minute last time. So at the end, this is just really a scikit-learn pipeline. So far, there's nothing distributed here. Here we go. So it took some reviews at the input. It took some ratings at the output, and it tried to find a pipeline that fits the reviews with the ratings. OK, so it took about a minute here. And most of the time was spent on running different experiments on this for this linear regression algorithms. So I'm going to use instead another version of this grid search algorithm. And that one has the same API, but it uses Spark under the hood to distribute all the computations. And the same thing as before. I'm going to have the same parameters. I'm going to use, again, the pipeline. All I switched at the end was here to say, I'm going to run this different experiment on Spark, but otherwise, this is exactly the same code. OK, let's fit it. So here you can see how it is running a number of experiments in parallel. And it should be done, It takes about 8 seconds to run. So what happened here is that it took the data that came in from that stage, sent it across the Spark cluster, and then returned the best model, the best pipeline it learned from the different stages. And this is again, and after that, this pipeline that we learned here is again a pipeline that is local, and you could move on to do your data analysis tasks. So then we could continue, we could extract the best estimator we got, and then we could move on with our analysis. So you see here, the only way, the only proof really that Spark was used is that here I've had to pass the Spark context that orchestrate the computations. But otherwise, this looks really similar to a single machine code. And this is the goal here. The goal is to make sure that if you are using these kind of primitives, you can distribute computations only when you need to. And otherwise, you can reuse exactly the same template that you have for doing local computations. OK, so we could use some distributed data sources here. The API looked strikingly similar between the two versions. And we could just distribute the one piece that was causing us trouble. However, there was still one issue with which I haven't addressed, which is running the same code between the production environment and what we're doing with. what we were building here. So this is one of the reasons why we see a lot of people actually using MLlib in practice, so the machine learning component of Spark, especially now that the MLlib features prominently the data frame API, also called the pipeline API, that lets you build full machine learning pipeline within Spark and MLlib. So the data frames used by Spark are very similar to essentially SQL or a similar version of SQL tables, distributed SQL tables, or if you're familiar with Pandas data frames or R data frames, it is simply a distributed versions of these data frames. And all the operators of MLlib let you combine and the pipeline API let you combine different machine learning operators that pass from one to the other these Spark data frames. And especially now in Spark 2, this data frame API is going to become the primary API for MLlib. This choice actually was endorsed by the community. And if you're using Spark for doing machine learning, you'll see most of the algorithm now being developed under these packages. So if you have been using older version of Spark, you should know that the RDD-based API is not going away. It will simply be less developed than before, but we're definitely planning to maintain it and add bug fixes to it. So you can still have access to it, and there are some layers, and you can actually convert back and forth between the two APIs. So one of the big features that came with this machine learning pipelines coming with Spark was the ability to persist data and to persist your pipeline. And this is one of the reasons we see why people are switching from the older API to the new one, simply because it lets you, on one side, having the data science team write a pipeline, express the algorithm, train them, and then you can take these pipelines that you have trained, give them to some other teams that run, so for example, on the production data, and they can take care of deploying that. So why usually there's this gap? Usually we see it because people tend to use Python and R, for example, to create models on one side, but these models are not usually something that you can use in the production environment, because usually the production environment works with Java or with some other technologies based on Java or C++, and usually we see some people taking the model they trained and rewriting it on the to make sure and completely rewriting it in the production environment. So with the usually the data science team also has all the tools it needs to build these pipelines, and these tools are not available necessarily on the production side. So as you can of course imagine, there is always some extra implementation work, some sanitation happening, and since there are different code paths, it's very easy to make a mistake on one side and forget to, for example, to fix a bug on one side, but forget to inform the other side that it needs to be fixed as well. So there is definitely some big synchronization overhead. So with the persistence API, you can do all the prototyping you want by data science, and you can write a pipeline or persist it. And then this pipeline is also available afterwards in Scala or in Java, because underneath they use the same implementation, and you can deploy this pipeline in production. So we have seen a couple of people in the community actually accessing the pipeline API using Python and R to train their model, and then transferring the learned model then to a Scala or Java environment. And so since it is the same implementation in between, it simplifies a lot some of the issues related to deployment. So it has been one of the big efforts for Spark 2, and it is now, we have near complete coverage for all these, so for the 3 supported languages, so R, Scala Java, and Python. And we have nearly complete coverage for all the algorithms available in Scala and Java. For Python, there are still a couple of remaining ones. And for R, all the APIs that were available now can use also the pipelines. And this is only possible because under the hood, all the algorithms are written in Scala and happens to have some bindings available through different languages. So actually a lot of care has been taken in making sure that the behavior across the different languages is consistent, which is not necessarily a given because each of the languages have different assumptions, different programming models, and sometimes very different runtimes. And making sure that they have consistent behavior between the 3 languages was, and it is still quite a significant effort. And of course, if you're unhappy with the implementation that we provide, you can always read the JSON, which is available, and also and then re-implement some of the algorithms. So using MLlib, so you can run your GIL code in a production environment. So you can, for that, use the pipelines. You can export these pipelines using MLlib in a format that then you can read again using other tools. And then we can also still, using Spark, we can use all the distributed data sources, and we can still reuse some of the APIs that we know about. So that was for Spark 2, which is going to come anytime soon now. What is the plan now for Spark 2.1 as far as machine learning is concerned? First, the most important feature is to make sure that all the different languages have the same set of features, and we aim at having full completeness and full parity between the languages for Spark 2.1. One major effort that we would like to have now that we have this common API based on data frames is to start to rely on the Tungsten engine that powers Spark to do some low-level optimization of the algorithms, and to make sure essentially that all the algorithms within MLlib are running as fast on a single machine as they would with existing solutions just based for single machines. So right now we are deciding which algorithms we would like to optimize for that. It will probably be decision trees and random forests, so ensembles of methods. And finally, there has been also a lot of work on providing a data frame-based API for graphics, so the graph component of Spark. And so a release is available as a separate project, and some more speed improvements will be available that also rely on the SQL engine of Spark, on Catalyst. So if you want to get involved, you are more than welcome to join us for Spark 2.1. And you can take a look at the main Jira that describes the roadmap, and also you can get involved in the mailing list. There is a couple of, and we also explain more details about the persistence on some blog posts. And also, if you want to try out the Spark 2 without having to compile it, or without having to do more experiments with it, if you don't want to do it locally, you can simply go to Databricks, and it is available as a preview in the community edition. All right, thank you for your attention, and I think now we have a few minutes for the questions. Over there. Yeah.
Hi. Okay. I actually have a question about integrating Spark and TensorFlow, one of the slides you were showing. Yeah, I was not, because it seems like the TensorFlow and Spark can do the same thing. So why you would ingest TensorFlow in Spark? I was not clear.
Oh yeah, so the question is, why use Spark with TensorFlow since they seem to achieve the same goals? Well, so Spark is a more general data processing engine, and TensorFlow is really specialized on manipulating tensors. And so this is why it makes sense to try to use really the framework at its best for each of the scenarios. And you can use Spark for doing all the ingest, and talking to HDFS, all these complex data sources for which there is no input for TensorFlow. Do some pre-processing using Spark. And then once you want to do the actual number crunching, which is usually a small part of the whole pipeline, then you can rely on TensorFlow for doing that.
When you say tensor, when you say tensor, you mean this two-dimensional matrix or?
So by tensor, I mean it's so either a matrix or a one-dimensional vector or even three-dimensional cubic data. Essentially, all sort of numerical data sets.
Multi-dimensional.
Exactly, and well, the Spark and the SQL engine can handle strings and complex structured and more structured data for doing that.
All right, thank you.
There were some questions. Yeah, we can. I guess we can move our way forward after that. Let's take this question and then that one.
So you had the transition from talking about using TensorFlow with Spark to using Scikit-Learn with Spark to using the ML that's built into Spark. And you mentioned some similarities between the API and Scikit-Learn and Spark. Are they both using the same engine under the hood?
So actually no. So Scikit-Learn was designed as a machine for doing for a single machine, and it has a very limited notion of distribution just based on multiple threads, and it assumes it can do some random access of data all locally. Spark is much more general for that and can talk to different computers with all the problems that come with it. So this is why the integration between the two happens just as a library. So you can either use Scikit-Learn as a subcomponent when you have a small data set that you can distribute, or if you have a pipeline, as I was mentioning, or if you have a pipeline that fits onto your local machine, but you want to parallelize some of its computations, then you can use Spark you can use the Python API of Spark to distribute these computations.
Yep.
Let's see. Yeah, there was a question.
Thank you.
Yeah.
It's not a machine learning question, but in general, Databricks question. The sheets, in order to use the sheets, right now the only option is that we have to come to your cloud to use it. Is there a on-prem option for enterprises to use something similar to Jupyter or some other form of using Databricks sheets, but in our own on-prem environment?
So for now, being able to run the whole solution on the cloud simplifies quite extensively the management we have to do for the different customers. So for now, I don't think we plan to have a solution for on-premise, but I'm happy to talk more about you if you. I'm happy to talk more.
Being a financial institution, we're concerned about the data moving to the cloud, so we rather bring the analytics to the data. So we would like to use Databricks, but it just becomes a little bit difficult for us to go move our data there.
Okay, I'll be happy to talk more about your problems later for moving the data around. Any other questions? All right, thank you.